Today we're going to do some practice. We have several different solids written here on the left-hand side of the page, and we're going to classify the force that holds those particles together as either London dispersion forces, remember that's between nonpolar substances, dipole to dipole, between polar molecules, hydrogen bonding, a special type of dipole to dipole where hydrogen needs to be bonded to nitrogen, oxygen, or fluorine in the molecule. Ionic, that's an easy one to identify. That's a metal bonded to a nonmetal. Metallic, another easy one to identify because that would just be a metal substance, wouldn't it? Silver, gold, zinc, copper, etc. And then finally, network covalent. It's the strongest of all force of attraction. They're covalent bonds between atoms or molecules, so those are really hard to break, and that mainly occurs in different elemental forms of carbon. We call those allotropes of carbon, or basically silicon-containing compounds. For this class, that's all you need to know. All right, so here we go. Let's start off with xenon, elemental xenon. How would xenon atoms be held together in this solid state? Well, it's certainly not hydrogen bonding. Good job there. It's not ionic. It's not metallic. It's not network covalent because it's a gas at room temperature, really, really low, boiling and melting point. So you have either LDFs or dipole to dipole. Is xenon by itself polar? No, it's not. So you're left with one choice. So did you choose LDFs? If you did, pat yourself on the back. Next up, magnesium. How are magnesium atoms held together in the solid state? That should be a gimme. Yeah, magnesium's a metal, isn't it? So magnesium atoms are held together by metallic bonds. Methanol, CH3OH. Okay, let's do the process of elimination game again. It's not metallic, we know that because it's not a metal. It's not network covalent, it's not an elemental form of carbon or a silicon compound. It's not ionic, we don't have any positive and negative ions there. Oh, what about hydrogen bonding? Is hydrogen bonded to oxygen there? It is. So those would be held together by hydrogen bonds. Okay, next up, NABR, sodium bromide. What do you think? NABR. It's not metallic, good job. Not network covalent. Not an LDF. Yeah, this is a metal bonded to a nonmetal, isn't it? So did you choose ionic bonding? Good. Next up, SiC, silicon carbide. Okay, that's a silicon-containing compound. Did you jump right to network covalent? If you did, good for you. Very, very high melting and boiling points for that substance. Those molecules are actually held to each other, not by LDFs, but they're held to each other by covalent bonds. Okay, HF, hydrogen fluoride in the solid or liquid state. They're held together by, yeah, you're getting good at this, aren't you? Hydrogen bonding. So hydrogen bonds. So if you'll notice, that one's an easy one. Isn't hydrogen bonded to fluorine there? Yeah. So those would be held together by hydrogen bonds. CaCl2, calcium chloride. Calcium chloride. Isn't calcium a metal? Isn't chlorine a nonmetal? Good job. Ionic bonding. We're on a roll here. All right, next up. Let's see if we can get the next one. I2. What do you think about I2? We're down here, kiddos. Yeah, that would be nonpolar, wouldn't it? So it would be LDFs. Certainly not ionic. That would be a metal to a nonmetal. It's not network covalent, right? It's not metallic. So it's either going to be hydrogen bonding, dipole to dipole, or LDFs. And it's not hydrogen bonding or dipole to dipole. It's not polar, is it? So you have to choose LDFs. Au, gold. 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 Yeah, that's a metal. So hopefully you said metallic bonding. Graphite. Yeah, that's an allotrope or elemental form of carbon. So did you guys say network covalent? And then finally, the last one on our list here, NCl3, nitrogen trichloride. Okay, good. It's not network covalent. It's not metallic. Excellent. So far, so good. It's not ionic. Good. It's not a metal to a nonmetal. So now we have three choices. It's either going to be LDF, dipole to dipole, or hydrogen bonding. Very good. Let's get rid of hydrogen bonding because hydrogen's not bonded to N or F there. So it's either going to be LDFs or dipole to dipole. So let's draw the Lewis structure for this one because we have to see if it's polar or not, don't we? And so here is NCl3. Do you remember the shape of this guy? Yeah, that lone pair is pushing the chlorines down into a trigonal pyramid shape, isn't it? It's not symmetrical. So that means this is polar. So what holds polar molecules together? Very good. Dipole to dipole. All right, hopefully you got most of those right. If not, you figured out your mistakes. And hopefully you'll be able to identify these in class on a quiz or maybe an exam. All right, good job today, kiddos. We'll see you soon.